My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 607. In this lecture, I will continue my discussion on convolution layer in neural networks. Before understanding this lecture, I request all of you to go through my previous lecture, that is 606. First you compute your convolutions, isn't it? Then you apply your element wise ReLUs, isn't it? There are two steps. Your step one is apply convolution and your step two is perform element wise activation like ReLU. This whole thing is often written as one step. It is not often shown as two steps. It is often shown as one step. Oftentimes, people used to write it as one step. This is my, what is this? Just see step one and step two. How people often used to write in one step, isn't it? This is my input image. This is my input, which is my n cross c. Let's assume I have m. Let's assume I have m k cross c kernels. Let's assume I am doing sufficient padding. Let me say I have sufficient padding and stride s equal to 1. And let's assume my activation is, what is my activation? Activation is ReLU, isn't it? The final tensor I will get. So what am I doing? First I perform my padding. Step number 1, perform padding. Then I perform m convolutions in step 2. M convolutions using this stride equal to 1. Then that is step 2. Step 2 is I am doing, first step is first I perform padding, that is step number 1. Then I perform m convolutions. Why? Because I have m kernels, k cross c kernels. Then in second step I perform my m convolutions using this stride s equal to 1. Then my third step, what will I do? Then apply my ReLU. So first padding, step number 1, first padding. Second, what is second is convolution, isn't it? Convolution with stride. Third is taking ReLU. And I get, what is the output of this one? I will get n cross m, because I have m kernels here, isn't it? And the size is, what is this size? Size is n cross n. Isn't this size? I have m kernels, and this size n cross n need not always be same. I have n cross n in input as well as I have n cross in output. These need not be same, isn't it? Just see here, what is my input size? N cross c. Here n cross n. This n cross n in input image as well as in output image, this n cross n, these two need not always be same, because if I change my padding, what happens? If I change my padding or if I change strides, isn't it? If I change my padding or if I change my strides or if I change my kernel size, this n cross n will change to, this particular n cross n will change to some other value. This n cross n will change to some other value. When will it change? If I change my padding, if I change my stride, if I change my kernel, this n cross n will change to some other value. This is one layer, is called a convolutional layer. So convolutional layer literally has two operations. What are those two operations? Convolution with multiple kernels followed by ReLU. And what is convolution? Convolution exactly like dot product, that the relation, convolution is just like dot product, isn't it? That's the relation between multilayer perceptron and coordinates that we learned in our previous lecture itself, isn't it? Very, very interesting. Now let me show you a very very interesting example. This is very simple coordinate. Just see this. I want to show you an example how ConNet work, isn't it? I suppose this is an input image. Let me assume this is simple ConNet. This is suppose this is an input image. Actually, this is a very nice tutorial at Stanford, isn't it? It is from Stanford. I will provide a reference link in the description section. This is one diagram I wanted you to explain. This is very high level explanation. I will show you why multiple levels of convolution is important, isn't it? Why multiple levels of convolution is important. So what happens in practice is people actually train multiple layers of convolutions, multiple levels of convolution. This is my input image. Let me say this is my input image. They perform one level of convolution followed by ReLU, isn't it? One level of convolution followed by ReLU. I get one more tensor. This is my input. What is my, I have input image here. Just see. This is my input, isn't it? This is my input. I get a tensor. What is the output? I am getting a tensor. Again, I apply convolution followed by ReLU. I get one more tensor, isn't it? So on and so forth. There is also an operation called pool. What is pool? We will try to understand. I will explain you what is the pool operation is in the next videos. But otherwise, just see that architecture. This is very rough example. Given an object, what you have to do? Given an object, just say this one. Given an object, suppose I have multiple classes that I wanted to determine. Whether it is a car, isn't it? Whether it is a car, truck, airplane, ship or horse. So this is like multi-class classification, isn't it? So what I have here, last layer. What is this last layer? Last layer, it is a fully connected layer with sigmoid activation or with softmax activation, to put it more simply, isn't it? So the typical architecture, I will show you, this is a typical architecture. I will show you more real world architecture, but this is only for understanding, isn't it? First apply convolution followed by ReLU. This becomes, just see here what's happening. Just I am applying convolution followed by ReLU, isn't it? This becomes one convolutional layer. Just see, this becomes one convolutional layer. Just see again what I am doing, convolution and ReLU. This is another layer, isn't it? Again after that pooling, again convolutional ReLU. Again this is first one, this convolution ReLU, it is layer 1. Just see, this is layer 1. Again convolutional ReLU, that is layer 2. Just try to understand this. Just see this one, convolution and ReLU, layer 1, convolution and ReLU, it's a layer 2. Again after that, what am I performing here? Pooling. Anyway, I will discuss about pooling in next videos. This is layer 3. Why? Because it's convolutional and ReLU. Here also I have convolutional ReLU. Again I have pooling. Here convolution ReLU, pooling. Isn't it? What is this? This is again FC basically means, just see what is my FC. FC means what? Fully connected, isn't it? Fully connected layer at the end. I will show you a real world example. This is how a real ConNet actually looks like, isn't it? A real ConNet, actually this is how a real ConNet, convolutional neural network, actually looks like. It has multiple layers of convolution with an operation called pooling. That, isn't it? It has multiple layers of convolution with an operation called pooling. That we will see in one of the next videos. But you might wonder, why do we care about it? This is a very nice presentation provided by people actually invented, like this is just Wai Kun, isn't it? And others terrifying team of researchers typically called God. This Wai Li Kun is typically called godfather of modern deep learning. They actually invented the whole CNN, isn't it? So this is a nice presentation in 2015. This is a nice presentation, Jesse. This is nice presentation in 2015, and this is a PPT. I will provide you a reference link in description section. Their observation is just like the brain, isn't it? Just like the brain. Observation was this. Their observation was this, just like the brain. Remember, what is the brain? What is the brain doing? I have the raw image. Let me say I have the raw image, isn't it? This is my raw image. That my eyes see, isn't it? V1 was detecting, let me assume V1 was detecting edges, V2 was detecting shapes and motions, things like that, so on and so forth. In the last layer, what happens? In the last layer, somewhere here, I actually do object recognition. So what they realized is when they build hierarchical system like this, let me say we are building hierarchical system like this, the output here is related to V1. You have input image and you are getting tensor. This output image, that output is related to V1 activation, and another output is related to V2 activation in the human visual cortex. So what they realized is very interesting. Given this image, my first level, I have all my kernels, isn't it? I can visualize my kernels, isn't it? I given what's happening? I given this image. Let me say I have a core image. My first level, I have all my kernels. I can visualize my kernels, isn't it? When we visualize the kernels that we learned at the end of the training, just see this kernel. It is literally doing edge detection. What's doing here? It's doing edge detection. This is edge. Here it is detecting one edge. Just observe. Here it is detecting some edge like this. This is even it is detecting like horizontal edge, isn't it? This is detecting angular edge. This may be the angular edge. This is detecting angular edge detection. This is also edge detection. This is looking for two edges. Just see here, I have two edges like this, isn't it? You have multiple edges also, isn't it? True edge detection. In the initial layers of my neural network, in my CNN, if I visualize my kernels, they look like edge detectors. That's important, isn't it? In my CNN, if I visualize my kernels, they look like edge detectors, isn't it? But when I go to that is in initial layers, but when I go to the higher levels, it start detecting parts, isn't it? Just see, this is it's detecting like tire. Just see, this is car tire. Just observe this one. Here I have car tire. It is detecting objects. It's a tire. It's look at this. This is tire here, isn't it? This is probably just see the body part. Here it is something like in next layers. What is it's detecting? Here it's a body part. It is just like detecting body part. So what's happening is, so when you train a convolutional neural network, which is hierarchical, just like in the brain, or very similar to the way the brain is working. Mathematics of the brain is far more complex because we have been inspired by brain. What people realized is one should train a convolutional neural network which is deep. When you train a deep convolutional neural network with multiple layers of convolution, the starting layer, what happens? The starting layers learn edge detectors, but the more complex layers learn parts, isn't it? More complex layers learn parts, even more complex layer learn parts, or even more complex layer, it looks like, just see, layers learn parts, isn't it? Flower, complex layers may detect things like flower. This is look like faces. It will detect flowers and faces. So more complex layers are learning more complex abstractions of the images. So initially they are, just observe this one, image recognition. Initially they are pixels, then it does edges, then it does text on, then it does motif part, and finally object itself. So if we train deep multi-layer convolutional neural network, whenever we say cornets, what it means? It means actually deep. Shallow cornets are very rare nowadays. So if you can train deep multi-layered convolutional neural network, it behaves very similar in its output to the visual cortex, isn't it? How the visual cortex is working? The visual cortex, isn't it? V1, V2, it's working like hierarchical manner, isn't it? Just try to recall, we recorded lecture on visual cortex. This could be my input tensor, isn't it? I can have one level of convolution with some parameters on it, convolution followed by the ReLU activation. I get one more tensor here. I can apply convolution on top of it. Again, I will get a different tensor, isn't it? I can keep getting tensors here. Eventually, what will happen is I will show you some example. Eventually, this tensor will get small enough, and we will perform an operation called flatten, isn't it? We will perform an operation called flatten. I will explain you flatten operation when we see actual real world neural network called LeNet. We will discuss this particular LeNet. The stacking of one layer on top of the other layers is critical for whole of the convolutional neural network. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.